Hi everyone, welcome to goclasses. In this lecture, we will solve gate previous year questions from this topic SDT, syntax directed translation or syntax directed translation scheme. In the previous lecture, we have seen the concept of all the concepts related to syntax directed translation scheme we have already seen in the previous lecture. Also, we have done some gate PYQs in the previous lecture. In this lecture, first we will do the revision of the concepts of syntax directed translation scheme, and then we will solve all the remaining gate PYQs based on it. Okay. So let's do some recap. In the previous lecture, all these concepts we have seen. So let me just revise them. You can see the lexical analyzer for the purpose of lexical analysis. It uses a specification, or I can say it uses a tool or formal mechanism that is regular expression. Similarly, the parser, or I can say syntax analyzer, for the purpose of syntax analysis, it uses a specification, or I can say a formal mechanism or a tool that is context free grammar. Similarly, the semantic analyzer, for the purpose of semantic analysis, to do the semantic analysis, the semantic analyzer uses a specification or formal mechanism or tool that is SDD or SDT. These are different. SDD and SDT, they are basically different concepts. They are related, but they are different concepts. In the previous lecture, we have already seen all the concepts related to SDT. Okay. So in the previous lecture, we have seen SDTS means syntax directed translation scheme. In short, you can write it SDTS, or you can write it SDT, or you can simply call it translation scheme, or you can simply call it syntax directed translation. So what is this SDTS, or I can say syntax directed translation scheme? What is this? The definition is very simple. Syntax directed translation scheme. This is basically a context free grammar with program fragments embedded within production bodies. These program fragments, these are called semantic actions, and they can appear at any position within the production body. So you can see, let's assume this is a production. You can see A going to XY. This is the production. So here the production is basically A going to XY. And in this production, in any production, the left side, that is called head. Okay, this is the head of the production, and this is the body of the production. Okay, correct. So you can see that this syntax directed translation scheme, what is the definition? The definition is very simple. This syntax directed translation scheme, SDT, this is a context free grammar with program fragments embedded within production bodies. So in this production body, we embed program fragments. These program fragments are called semantic actions. So basically, the semantic actions can appear at any position within the production body. Okay, at any position within the production body, this semantic action can appear. You can see semantic action can appear here, or between X comma Y, or at the right end of the production body. Okay, very simple. Now let's see how to evaluate SDT. You can see evaluation of syntax directed translation scheme. If a SDT is given to you, if a syntax directed translation scheme is given to you, then how to evaluate, or I can say how to execute it. So the idea is very simple. The idea is basically that the the position of semantic actions in the production body determines the order in which the action is executed. So basically, the order in which semantic actions will be executed, that order is determined by the position of semantic action in the production body. Okay, the position of the semantic action in the production body, it will determine the order in which semantic actions are executed. Now let's see the general method to evaluate any SDTS, any syntax directed translation scheme you have. Then what is the general method to evaluate it? Very simple. Any SDT can be evaluated by first building a parse tree. First you build a parse tree with nodes for semantic actions too. When you are making the parse tree, then for the semantic action also you make nodes in the parse tree. Okay, basically these semantic actions, you consider them like the leaves. Okay, or you consider them like the terminals. Okay, so including the semantic actions, you make the parse tree. Then what you do, Once your parse tree has been built, then you perform, then you execute the semantic actions in the left to right depth first order. That is pre-order traversal. Basically, once you have built the parse tree, then basically you go left to right depth first. Okay, we will go left to right depth first, and when you are going left to right depth first, then as soon as you reach a semantic action, immediately execute it. Very simple. Okay, so you can see we will execute the semantic actions, we will perform the semantic actions in a left to right depth first order, that is pre-order traversal. During left to right depth first order, as soon as you reach a semantic action, immediately execute it. Very simple. Okay, so this is the general method to evaluate any SDT. Okay, so you can see this is what we have seen here, that semantic actions, we will treat them as terminal symbols. In this general method of evaluation, any SDT is given to you, then how to evaluate that SDT? So we will consider the semantic actions, we will treat them as terminal symbols. You can see an action may be placed at any position within the body of the production, that we already know. It is performed means it is executed immediately after all the symbols to its left have been processed. What it means? It means that, let's assume this is the semantic action. You can see B going to XY, this was your production. B going to XY, this was your production. And you can see at this position, we have put this semantic action. This semantic action we have put here. So here you can see that we are putting this semantic action A. Okay. Between X comma Y, we are putting this semantic action A. So you can see that if we have this production B going to X, then this semantic action A, then Y, then you can see this action, this semantic action A will be executed. This semantic action A will be done after we have recognized X. Means basically after X and before Y, this semantic action will be executed. Okay, so you can see after you have recognized X, or I can say that after all the terminals derived by X have been recognized. Basically, once you are done with X, okay, once we are done with X, then this semantic action A will be executed. So you can see this semantic action A will be executed once you are done with X and before Y. Okay, so you can see that position of semantic action is telling you the order in which the semantic actions will be executed. The position of the semantic action is telling you when this semantic action will be executed. Okay, I hope you understood. Very simple. Now let's see what is postfix SDT. That is postfix translation scheme. This is another name for postfix SDT. So this is a special type of SDT, and this postfix SDT, this is basically most commonly used SDT type. Okay, that is the reason we are studying this separately. All these concepts we have seen in the previous lecture. This is just a recap, nothing else. Okay, now once this recap is done, then we will solve the gate PYQs. Okay, so you can see this postfix SDT, this concept also we have seen in the previous lecture. What is this postfix SDT? This is a special type of SDT, and we study this because this is the most commonly used SDT type. Okay, so let's see what is the definition of postfix SDT. The definition is actually very simple. SDT in which all the semantic actions are placed at the right end of the production bodies, these are called postfix SDT. The name itself is telling you postfix SDT means all the semantic actions, they are at the right end of the production bodies. Okay, means the semantic actions cannot be between two terminals. Okay, the semantic actions cannot be placed between the production body. The semantic action must be placed at the right end of the production body. Okay, so you can see here some SDT are given to you. Which of them is postfix SDT? So here you can see that, look at this SDT. Here, this semantic action, this is not at the right end of the production body. Actually, this is in the middle of the production body. You can see after plus T and before R. So you can see this semantic action we have placed in the middle of the production body. So this SDT, this is not postfix SDT. This is a SDT, but this is not postfix SDT. Okay, look at this SDT. Here all the semantic actions are placed at the right end of the production bodies. So you can see this is actually postfix SDT. What about this SDT? Is this postfix SDT? Yes, this is also postfix SDT because all the semantic actions they are placed at the right end of the production bodies. And you can see what about this SDT? Here you can see this semantic action. This is not at the right end of the production body. Like this is also not at the right. This is also not at the right end of the production body. So basically, this SDT, this is also not a postfix SDT. Okay. I hope you understood the definition of postfix SDT. Now let's see how to evaluate postfix SDT. I told you that this postfix SDT, this is the most commonly used type of SDT. Okay, so we have a special evaluation method to evaluate postfix SDT. If you want to evaluate postfix SDT, either you can use the general method, but there is a special method only for postfix SDT. So whenever a postfix SDT is given to you, then you can use this specific method designed only for postfix SDT, or I can say this specific method, this specific evaluation method, which is only applicable on postfix SDT. Okay, so let's see what is that. Now you can see why postfix SDT are special, because in postfix SDT, the semantic actions can be executed along with the reduction of the body to the head of that production. What it means? It means that in this, in any postfix SDT, a bottom parser or a LR parser, it will carry out the semantic actions immediately after reducing the corresponding production. Okay, so this is how you can understand this postfix SDT evaluation. So if a postfix SDT is given to you, then how to evaluate it? It is very simple. You can see that a bottom-up parser or LR parser will carry out the semantic actions. It will execute the semantic actions immediately after reducing the corresponding production rule. Okay, in simple words, I can say that in postfix SDT, along with reduction, you can perform the corresponding semantic action. Okay, in the previous lecture, we have seen multiple examples. We have seen some gate PYQs also. So this is just a recap, but I hope you understood that how to evaluate postfix SDT. Very simple. In simple words, I can say that in postfix SDT, we can execute the semantic actions along with the reduction of the corresponding production rule. Okay, when you reduce a production rule, then along with the reduction, or I can say immediately after the reduction, you can perform the corresponding semantic action. Very simple. Okay, so you can read this evaluation of postfix SDT. Postfix SDT, this is also called postfix translation scheme. So let's see evaluation of postfix SDT. What is that? You can see given a postfix SDT, to evaluate such SDT, the best way is the following. So this is the method you can use to evaluate postfix SDT. Okay, so let's see what is the method, what is the best way to evaluate postfix SDT. That is, first you make a parse tree without semantic actions. Remember, in the general method, for all the SDT, whatever type of SDT is given to you, the general method, in that general method, we make a parse tree with semantic actions. Yes or no? But here, this is a specific method only applicable for postfix SDT. So given a postfix SDT, how to evaluate such SDT? The best way, that is, first you make a parse tree without semantic actions. Then what you do? Then we execute the semantic actions along with the reduction of corresponding production rule. When you reduce a production rule, then immediately after reduction of a production rule, you execute the corresponding semantic action. You perform the corresponding semantic action. Very simple. Okay. And let's see a note here. You can see if postfix SDT is given to you, then this method you can always apply. This is the best way to evaluate postfix SDT. But let me tell you, there is a particular situation where you must apply this method only. For postfix SDT, you must apply this method only. In which situation? So let me tell you, the above method is particularly best when given postfix SDT, when you are given a postfix SDT in which semantic actions compute the values of attributes of non-terminals. Means if a postfix SDT is given to you in which the semantic actions they are computing the values of attributes of non-terminals. Okay, a postfix SDT, some postfix SDT is given to you in which the semantic actions they are basically computing the attribute values. Okay, then for this type of postfix SDT, we we will apply this method only. Okay, to evaluate postfix SDT, this is the best method. I can say make a parse tree without semantic actions, then you execute the semantic actions along with the reduction of corresponding production rule. Okay, this is the very simple method. And in the previous lecture, 2 3 gate PYQs we have done using this method, also using the other methods also. Basically same question we have solved with multiple methods. Okay, now we are going to solve a lot of gate PYQs. Now let's start. Let's solve gate 2016 PYQ. You can see, consider the following syntax directed translation scheme SDTS with non-terminals S, A and terminals A, B. This SDTS syntax directed translation scheme is given to us. Okay, the question is saying using the above SDTS, the output printed by a bottom-up parser for input AAB. What is that? First of all, you notice this syntax directed translation scheme that is given to us. Is this postfix SDTS? Is this postfix SDT? Is this postfix translation scheme? Tell me. Yes, this is a postfix SDT. Why? Because you can see that all the semantic actions they are at the right end of the production bodies. Yes or no? The semantic actions, all the semantic actions they are at the right end of the production bodies. So you can see this is a postfix SDT. And when a postfix SDT is given to you, then how to evaluate this postfix SDT? The best method I told you. What is the best method? We will make the parse tree without semantic actions. We will make the parse tree. Then you can see what we will do. Then we will go left to right, depth first. Okay, we are going to go left to right, depth first. And when we reduce a production, then immediately after reducing a production, we will execute the corresponding semantic action. Okay, this is the simple method. I hope you understood. So you can see this method we have already seen that when a postfix SDT is given to you, given a postfix SDT, to evaluate postfix SDT, what we will do? First, we will make the parse tree without semantic action. Then what we will do? Then we will do left to right. Then we will go left to right. Then we will go left to right, depth first. Then we will do left to right, depth first traversal. Okay, and you can see we will execute semantic actions along with the reduction of corresponding production rule. Very simple. Okay, let me tell you this SDT, because this is postfix SDT, so you can apply the specific method for postfix SDT. You can apply that, but also you can apply the general method for all the SDT. That also you can apply. Okay, so this same question we will solve by multiple methods. So let's start. Let's solve this question using method number 1, that is general method for all SDTs. For all syntax directed translation schemes, this general method we have to evaluate any syntax directed translation scheme. What is the general method? It is very simple. You first build a parse tree including the semantic actions. Okay, with semantic actions, including the semantic actions, you build a parse tree. Then you perform left to right, depth first traversal, and as soon as you reach a semantic action, execute it. Very simple. Okay, so let's see here. This is the given SDTS. This is the given translation scheme. And what the input? The input is double AB. This is the input. So you can see the input is AAB. So let's see in this method number 1 what we are going to do. In the method number 1, we will first build parse tree, including the semantic actions. We will make nodes for semantic actions too. Okay. So very simple. Let's build the parse tree. The root node, the root node of the parse tree, that is basically the start variable, that is s. Okay. So you can see we want double ab. So this s will go to a print 1. Notice one thing in this general method where we are making the node for semantic action also. So what you do, you treat the semantic action like a terminal. Okay, this semantic action, you treat this like a terminal. So you can see this s will go to a print 1. Okay, this s will go to a print 1. Okay, print 1. Now let me use a different color for the semantic action so that it can indicate that yes, this is a semantic action. So you can see this is actually a semantic action. But remember, in this method number 1, which is a general method, which is a general method for any SDTs, for any syntax directed translation scheme, this is the general method. In this method, what we do, we build the parse tree, including the semantic actions. For semantic actions, also we make node in the parse tree. Basically, in this general method, we treat the semantic action like a terminal symbol. Okay, very simple. So we are treating this semantic action like a terminal symbol. Okay. Next, you can see that we got our a, we also want ab. So you can see this a, this will go to sb, correct? But notice one thing here, this a will go to s b print 3. Okay, yes or no? Because in this general method we treat this semantic action like a terminal symbol. So you can see we will make node for this semantic action also. So this a will basically go to s b and print 3, print 3. Okay, very simple. Now, what about this s? This will go to a because we want AAB. Okay, so this s will go to a. So you can see this will happen that s will go to a print 2. Okay, this s will go to a print 2. I hope you understood. That's it. So you can see once the parse tree has been built, now what we will do? We will do left to right depth first traversal. Okay, and as soon as you arrive at a semantic action, execute it. Okay, very simple. So you can see that we will perform this left to right depth first traversal. Okay, so you can see this is the step number 1. Step number 1, parse tree, parse tree including semantic actions. Correct? Okay, including semantic actions. This is the step number 1. Now what is step number 2? The final step, the step number 2, that is basically you perform left to right depth first. Okay, depth first traversal. Left to right depth first traversal, I can say. Depth first traversal. Okay, and as soon as you arrive, as soon as you reach a semantic action, immediately execute it. Okay, so very simple. Let's see here. You are going left to right depth first. Okay, you are going left to right depth first, left to right depth first, and you can see that as soon as you arrive at a semantic action, immediately execute it. Okay, so you can see what will be our output. Our output will be, we will print 2. Okay, now you can see after printing 2, just keep going left to right depth first. Okay, keep going left to right depth first. You can see, keep going, keep going. As soon as you reach a semantic action, immediately execute it. Okay, so you can see print 3. Now keep going left to right depth first. As soon as you reach a semantic action, immediately execute it. Okay, keep going, keep going. Okay, that's it. So you can see our output will be 231. This will be the answer. Okay, the question is asking that using the above SDTs, the output printed by a bottom-up parser for the input double AB, what is the output printed? The output printed, that is 231. Okay, 231. The answer will be option C. So this is the method number 1, that is the general method for all syntax directed translation schemes. Okay. Now the same question we are going to solve using two other method, But these two other methods, they will only work for postfix SDT, because the given SDT is actually postfix SDT. All the semantic actions, they are at the right end of the production bodies. So this is a postfix SDT. Now for postfix SDT, we have a specific way of evaluation. Okay, so using that method, we are going to solve this question now. So you can see method number 2. This is only applicable for postfix SDTs. What is the method? Method is very simple. A bottom-up parser will carry out the semantic action after reducing the corresponding production rule. Very simple. Okay, means when you reduce a production rule, when we are reducing a production rule, then immediately after the reduction, you execute the corresponding semantic action. Very simple. Okay. Now, in this method number 2 also, there are two ways. Either we can solve the question using parse tree, or we can solve the question using rightmost derivation. Okay. In the previous lecture also, we have done 2 or 3 gate PYQs where we have seen this method to way 1, also method to way 2. Yes or no? So for this question also, just for sake of complete analysis, let's solve using method to way 1. Also, let's solve using method to way 2, means using parse tree as well as using rightmost derivation, just for understanding the concept. But remember, in the gate exam, we are going to apply this method to way 2, means using the parse tree. When postfix SDT is given to you, then what we will do, how to evaluate this SDTs? Very simple. We will make the parse tree without semantic actions. Then we will traverse left to right depth first. Okay, and then you can see that when you perform a reduction, then immediately after the reduction, you execute the corresponding semantic actions. Okay, so this method to way 2, this is particularly, I can say, based. This is, I can say, based for postfix SDT. Okay, postfix SDTs. But still, just for our learning, or I can say just for our understanding, let's solve this question using method to way 1. Okay, that is using rightmost derivation. So first what you do, you make the rightmost derivation. The input is double AB. Okay, let me number the productions. Let me call this production 1, production 2, production 3. Okay, now let's create the rightmost derivation. The rightmost derivation will start from the start variable. Okay, so you can see from the start variable, you can see we will apply the production number 1. S will go to A. Then you can see here we only have one non-terminal. So this non-terminal we need to expand. So you can see there is only one A production. So that we have to apply. So this production number 3 we will apply. You can see we will go to A, S, B. Then again we only have one non-terminal. So this S we have to expand. And we want this input A, B. So this S will go to A, means this second production we will apply. And we will get A, B. That's it. Okay, now you can stop. So this is the rightmost derivation. Remember one thing. This is the rightmost derivation. What the bottom-up parser will do? I told you, bottom-up parser will generate reverse of rightmost derivation. Yes or no? So the bottom-up parser will start from the string, and the bottom-up parser will reduce this string to the start variable. So basically the bottom-up parser, or I can say LR parser, bottom-up parser, or I can say LR parser, what it will do? It will start from the string. Basically, it will go in this order. Means whatever this rightmost derivation is doing, the bottom-up parser will do exact opposite. Whatever this rightmost derivation is doing, the same thing this bottom-up parser will do, but in the reverse order. Okay, so you can see what this bottom-up parser will do. Whatever this rightmost derivation is doing exact reverse of it. Means you can see this rightmost derivation is doing this, that S is going to A. This is what the rightmost derivation is doing. So what the bottom-up parser will do? It will reduce this A to S. Means the bottom-up parser will replace this A with S. Okay, and remember here, the bottom-up parser is applying this production in the reverse order. Means this A we are replacing by S. So when you apply a production in the reverse order, that is called reduction. I told you, applying a production in the reverse order, that is called reduction. So this is your first reduction, I can say. from the bottom up parser point of view, this is the first reduction. Okay, so you can see that this reduction we are performing. And I told you that how to evaluate postfix SDT. The method is very simple, that semantic actions will be executed immediately after a reduction. So basically, immediately after this reduction, which production we are reducing? We are reducing the second production. Yes or no? This A we are replacing by S. So this second production we are reducing. So reduction, here we are reducing the second production. So the corresponding semantic action we will execute. Is this clear? So you can see here we will reduce. Okay, so what we will do? The corresponding semantic action we will execute, means we will print 2. Okay, is this clear? So what will be the output? The output will be 2. What about the next? Next you can see, notice one thing. What will be the next reduction by the bottom up parser? I told you bottom up parser will do what this rightmost derivation is doing, but in the reverse order. You can see the rightmost derivation is basically replacing this A with SB. Yes or no? Okay, this A with SB. A with SB. So what this bottom up parser will do? The bottom up parser will replace this SB with A. Yes or no? So basically this SB you will replace by A. So you are applying this production in the reverse order. This is called reduction. Okay, and I told you that this method, evaluation of postfix SDT, this is applicable only for postfix SDT. What we do? The semantic actions are executed immediately after a reduction. So here this third production you are reducing. So the corresponding semantic action we will execute. So you can see immediately after this reduction, this corresponding semantic action we will execute, means we will print 3. Okay, very simple. Okay, I hope you understood. And next you can see that this first production we are reducing. So when you reduce this first production, then the corresponding semantic action you will execute. So you can see that at the end, this is the last reduction. Okay, this is the last reduction, I can say. And when you reduce, then immediately after the reduction, the corresponding semantic action we need to execute. So you can see this, here you can notice this production 1 we are reducing. So the corresponding semantic action we will execute, means we will print 1. Okay, we will print 1. So the answer will be 231. I hope you understood. Okay, very simple, right? So you can see the answer will be 231. Now let's solve this same question using the last method and the best method. This is the method that we will use for most of the questions, and this is the method that we will use in the gate exam. This is the method that you should use in the gate exam. Okay, so let's see this method. This is only applicable for postfix SDT. What we will do, step by step, what we will do? First we will create a parse tree without semantic actions. Then we will perform left to right depth first traversal, and you can see semantic actions will be executed immediately after reduction. Okay, method is very simple. So let's create the parse tree. So you can see the parse tree root node, that will be the start variable S. So this S will go to AA. Next you can see this A will go to SB. Next you can see this S will go to A. Okay, this is the parse tree because our input is double AB. Very simple. Now, once parse tree has been built, then what is the step number 2? This is the step number 1. Step number 1, that is parse tree, build parse tree. Without semantic actions. Okay. Without semantic actions, you just build the parse tree. Now, what is the step number 2? The step number 2, that is we will perform left to right depth first traversal. Okay, and remember, semantic actions will be executed immediately after a reduction. Okay, immediately after a reduction, semantic actions will be executed. This is what we are going to do. So you can see we will perform left to right depth first traversal. Okay, just keep going left to right depth first. Remember, this is not a reduction, right? A going to S, this is not a reduction here, because here, notice one thing, this AA is actually going to S, this is the reduction here. Okay, is this clear? Notice this A going to S, this is not a reduction here, because this AA will go to S, this AA will go to S, this is the reduction. Okay, so you can see, just keep going until you find a reduction. Okay, so you can see depth first, left to right, depth first, left to right, depth first. Okay, now you notice one thing here, that here this A going to S, yes, this is the reduction. Okay, A is reducing to S, this A you are reducing to S, so this is the reduction. This A you are reducing to S, and you can see that the semantic actions will be executed immediately after a reduction. Which production you are reducing? This production you are reducing, so the corresponding semantic action will be performed. So you can see the output will be print 2, that means 2 will be printed. Okay, yes or no? Very simple. So keep going left to right, depth first. Now notice here, again you can see that this is a reduction. What reduction? This SB is reducing to A, this SB is reducing to A, so this is the reduction. And you can see semantic action will be executed immediately after a reduction. So here you are reducing this production, so the corresponding semantic action will be performed, means print 3, we will print 3. Okay, keep going. Now notice, next you can notice, now again there is a reduction. What is that? Which reduction is this? This AA we are reducing to S, this AA we are reducing to S, so this production you are reducing, so the corresponding semantic action will be executed immediately after the reduction. So here this semantic action will be performed, means print 1, so we will print 1. Okay, so that's it. So the output will be 231. I hope you understood. So finally the answer is option C, but this question we have done using 3 methods. I hope you understood this. In the previous lecture also we have done some gate PYQs using 3 methods. This question also we have done using 3 methods. But let me tell you, because this SDTs, this is postfix SDT, so the last method that we have seen, that is the best method for postfix SDT. If the given SDT is not a postfix SDT, then the best method is the general method. Okay, is this clear? I hope you understood this. Let's solve this GATE 2022 question. Consider the following grammar along with transaction rules. Let's solve this GATE 2022 question. Consider the following grammar along with translation rules. Basically, this SDTS means syntax directed translation scheme is given to you. You can see the question is saying that this translation scheme is given to us. Okay, so this is syntax directed translation scheme. Now the question is saying here hash comma this percentage are operators. ID is a token that represents an integer. ID dot value represents the corresponding integer value. The set of non-terminals is strp, and subscripted non-terminal indicates an instance of that non-terminal. For example, here you have T1. Notice this T1 is same as T. Both are the non-terminal T. There is no non-terminal T1. You don't have any non-terminal T1. But remember, here you are using T1, here you are using T. Why? What is the reason? So that we can differentiate which T you are talking about, the left T or the right T. Okay, so you can see to differentiate that, okay, in this production which T I am talking about, that is the reason this subscript we are going to use. Okay, so you can see this subscripted non-terminal indicates an instance of that non-terminal. So the non-terminal is same. This is also T, this is also T. But just to differentiate between these two T, we are using this subscripted non-terminal. Okay, very simple. Using this translation scheme, the computed value of s.val for the root node of the parse tree for the expression, this expression is given to you. For this expression, we make the parse tree, and then for the root node of the parse tree, we need to compute the s dot val, this value you need to compute. Okay, I hope you understood the question. Now, once you understood the question, now we can easily solve it. First, you tell me this given SDTs, this given translation scheme, this given syntax directed translation scheme, is this postfix SDT? Let me know. Is this postfix SDT? Yes, this is postfix SDT. Yes or no? Because all the semantic actions, they are placed at the right end of the production bodies. Yes or no? So this is actually postfix SDT because all these semantic actions, they are placed at the right end of the production bodies. And whenever postfix SDT is given to you, how to evaluate this postfix SDT? What is the method? The method we have already seen. You can see, given a postfix SDT, what is the method to evaluate a postfix SDT? Very simple. First, we will make a parse tree without semantic actions. Then what we are going to do? Then we are going to perform left to right. Then we are going to perform left to right, depth first traversal. Okay, and then you can see we will execute semantic actions along with reduction of the corresponding production rule. Okay, very simple. And I told you that this method to evaluate postfix SDT, of course, this method is applicable only for postfix SDT, and this is the best method to evaluate any postfix SDT. And this method is actually particularly based when the given postfix SDT computes the values of attributes of non-terminals. Look at this postfix SDT. Here, you are computing the attribute values, yes or no? Like, for example, this is the attribute of non-terminal S, this VAL. This is the attribute of non-terminal S. This is the attribute of non-terminal T. This is the attribute of non-terminal R. So here, basically, in these semantic actions, you are computing the attribute values of the non-terminals. So in this particular situation also, this method becomes, I can say, more better. Okay, or I can say the best. So this is the best method to apply when you need to evaluate postfix SDT. Okay, so let's solve this question now. The method you already know. Now let's solve this question. So we need to translate this input. The input is given to you. So first let me write this input here. The input is basically 20 hash 10 percentage 5 hash 8 percentage 2 percentage 2. Okay, this is the input that is given to you, and we need to find what will be the translated output. Okay, using this translation scheme, using this SDTs, what will be the s dot value for the root node of the parse tree for this expression? Okay, so let's build the parse tree. That is the step number 1 to evaluate any postfix SDT. This is the postfix SDT. So how to evaluate this postfix SDT? We will build the parse tree without semantic actions. So for the parse tree, the root node will be the start variable, that is s. Okay, s. Now you can see s will go where? You can notice total we want 2 hash and 3 percentage. Okay, yes or no? And you can see this hash, only this variable s can give me hash. So you can see this s will go to s hash t. Okay, remember this s1 and this s, they are basically same non-terminal but different instances. Just to differentiate which s I am talking about, we are using this subscript, but actually both are basically the same non-terminal. So in the parse tree, you can directly write it as going to s hash t. Okay, you can write like this. So very simple. Now what next? Again, you notice we want total 2 hash. We already got 1 hash. We want total 2 hash. So again, you can see only this s can give me hash. Only this s can give me hash because t or r, they cannot give me hash. So you can see this s will give me hash. So another, this s will again go to s hash t. S hash t. Okay. What next? Now you can see we got 2 hash we got. So that's it. So now this s can go to t, this s can go to t, then this t can go to r, and this r can go to id, and that id, this id is a token, so what is the lexical value? That is 20. Okay, you can see this id, this is basically 20. Okay, very simple. Now let's see here where this t will go. You can see that between two hash, between these two hash, we need a percentage. Yes or no? Between the two hash, we need this percentage. So this t will basically go to t percentage r. Okay, so you can see this t will go to t percentage r. Okay, next you can see we got this percentage between these two hash, we got this percentage. Between two hash, we only need one percentage, so one percentage we got. So now you can see that this t will go to r and this r will go to id, and here what is the id, what is the lexical value for this id? That will be 10. Okay, so here this id is 10. Very simple. Next you can see this r, where it will go? This r will go to id, and this id, for this id, what is the lexical value? Because this id is basically the token that is written here. You can read this, that id is a token that represents an integer. Okay, and you can see what is id dot value, that represents the corresponding integer value. Okay, very simple. Now, so you can see, so here this id, this r is going to id, and here this id is the token. So what is the lexical value we need? We need 5. Yes or no? Okay, we need 5. So this will be 5. Okay. Next, what about this t? You can see to the right of hash, we need 2 percentage. Okay, so we need total 2 percentage we need. So let me do like this, that this s is going to t, and now this t, we need total 2 percentage we need from this t. So this t will go to t percentage r. This t will again go to t percentage r. T percentage r. Okay. Now you can see that this t will go to r. This r will go to id. And what is the lexical value for this token id? That is 8. Okay, that is 8. Next you can see this r will go to id, and the lexical value for this token id, that is 2, and this r will go to id, and the lexical value for this id token, that will be 2. Okay, I hope you understood. So finally you got this parse tree. Okay, once you got this parse tree, now what we will do? We will perform left to right depth first traversal, and along with reduction, or I can say immediately after reduction, we will perform the corresponding semantic action. We will execute the corresponding semantic action. Correct? First of all, you notice, is this parse tree correct? Is there any mistake here? You can see what is the yield of this parse tree, means which string is generated by this parse tree. So you can see that is basically 20 hash 10 percentage 5 hash 8 percentage 2 percentage 2. Yes, that is correct. Okay, so this parse tree is correct parse tree for this input. Okay, from this parse tree, if you find what is the yield of this parse tree, or what is the string generated by this parse tree, then that will be basically same as the input. Okay, so this is the correct parse tree. So this is, I can say, step number 1. Okay, this is the step number 1. Step 1, that is parse tree without semantic actions. Okay, now what is the step number 2? The step number 2 is basically you go left to right depth first. Okay, keep going until you find a reduction. Okay, just keep going until you find a reduction. Okay, keep going. So you keep going until you find a reduction. Now you can see that we found this reduction. Okay, so let me use this color. You can see we found this reduction. id is reducing to r. Correct? Yes or no? id is reducing, this id is reducing to r. So immediately after this reduction, we will execute this corresponding semantic action. Okay, so this corresponding semantic action because you are reducing this production, so the corresponding semantic action we will execute. So you can see this r dot value, it will become id dot value. Id dot value, that is already 20. So what will be, what will become r dot value? That also will become 20. Okay, yes or no? So you can see that here this r dot value will become 20. This r dot value, it will become 20. Very simple. Now again you keep going. Again we got a reduction. Yes or no? You can see r is reducing to t. Okay, you can see this r is reducing to t. So immediately after the reduction, you execute the corresponding semantic action. So here t dot value will become r dot value. Okay, so you can see that here t dot value, this t dot value, this will become r dot value. That is r dot value is already 20. So t dot value will become 20. Very simple. Next, you keep going. Okay, you keep going left to right depth first. Keep going until you find a reduction. Okay, keep going like this. Then you can see here you got your next reduction. You can see id is reducing to r. Id is reducing to r. So here immediately after this reduction, you will perform this semantic action. Corresponding semantic action we will execute. So the r dot value will become id dot value. Here id dot value, that is 10. So here r dot value will become 10. Okay, so let me write 10 here. Okay, next you can see keep going. The next reduction we got, this is the next reduction. R is reducing to t. Okay, you can see r is reducing to t. So immediately after this reduction, we will perform this corresponding semantic action. So the t dot value will become r dot value, and r dot value, that is already 10. So t dot value will also become 10. Okay, so for a moment let me write 10 here. That okay, this t dot value, this has become 10. Okay, then you keep going. Okay, you keep going left to right depth first. Okay, till you find the next reduction. Now you got your next reduction, that is id is reducing to r. Again id is reducing to r. So immediately after the reduction, we will perform the corresponding semantic action. So r dot value will become id dot value. So id dot value, that is 5. So r dot value will become 5. So here this r dot value, this will become 5. Okay, keep going until you find the next reduction. Now the next reduction is actually this. Which one? T percentage r. This t percentage r, this is reducing to t. Notice this t percentage r, this t percentage r, this is reducing to t. T percentage r, this is reducing to t. Okay, so immediately after the reduction, this semantic action, the corresponding semantic action you will perform. So you can see what this t dot value will become. This t dot value, this t, this is the head of the production. So you can see this t dot value, it will become t1 dot value divided by r dot value. So you can see t1 dot value, that is 10. Okay, yes or no? You can see here t1 dot value, that is 10. R dot value, that is 5. So what this t dot value will become, that is t1 dot value divided by r dot value. So that is 10 divided by 5, that is 2. Yes or no? So here you got 2. Okay, very simple. I hope you understood. Now again you keep going until you find the next reduction. Again you found the next reduction. You can see this is the next reduction. Which reduction is this? Which reduction is this? You can see that this s hash t, s hash t, you can see s hash t, this you are reducing to s. So immediately after this reduction, you will perform the corresponding semantic action. So this s dot value, remember s is the head and s1 is this. So you can see that this s dot value, this will be s1 dot value into t dot value. Okay, yes or no? Actually, one more thing here. Here, there was one more reduction actually, t going to s. There was one more reduction. We missed here. There was one more reduction here. See. Here, t going to s. This was one more reduction. T going to s. This t, this reducing to s. This was another reduction. So immediately after this reduction, this semantic action we will perform. So you can see this s dot value will become t dot value. Okay, so here you can see this s dot value will become basically t dot value. T dot value is 20, so this s dot value will become 20. Okay, this s dot value will become 20. Then you can see we will go like this. Okay, like this. Okay, very simple. Now anyway, so let's see this. You can see this s has t. Okay, you can see this s has t. This you are reducing to s. This s has t, you are reducing to s. So this s dot value, you can see s dot value, it will become s1 dot value, that is 20, into t dot value, that is 2. 20 into 2, that is 40. Yes or no? So here I can put 40, that okay, this value has become 40. I hope you understood. Okay, now let's keep going. Keep going. I hope you understood the process, I can say. Okay, just keep going until you find the next reduction. Now you can see that we found our next reduction, that is, this is the next reduction. You can see id is reducing to r. id reducing to r, this is the next reduction, correct? id is reducing to r. So immediately after the reduction, this semantic action, the corresponding semantic action we will execute. So you can see r dot value will become id dot value. Here id dot value, that is 8, so r dot value also will become 8. Okay, yes or no? So here r dot value, that will basically become 8. This is basically 8. Okay, now keep going until you find the next reduction. The next reduction is actually r going to t. This is the next reduction. This r is reducing to t. So immediately after this reduction, this corresponding semantic action you will perform. So t dot value will become r dot value. R dot value is 8. So this t dot value, this will also become 8. Okay, keep going. Next, you can see that keep going. Keep going. Next, you can see this is the next reduction. The next reduction is id to r. So you can see the corresponding semantic action we will execute. So r dot value will become id dot value. Here id dot value, that is 2. So r dot value also will become 2. Next, you can see that again we got the next reduction. What is the next reduction? The next reduction is t percentage r is reducing to t. Okay, t percentage r is reducing to t. So the corresponding semantic action you will execute. So in the corresponding semantic action, you can see that t dot value will become t1 dot value divided by r dot value. You can see this t dot value, it will become t1 dot value, that is 8, divided by r dot value, that is 2. So 8 divided by 2, that is 4. So remember here, this t dot value, it will become 4. Okay, now keep going. The next reduction, this is the next reduction, and here r dot value will become id dot value, that is id dot value is 2, so r dot value will become 2. And then we have the final reduction, not final reduction, basically this t percentage r will reduce to t. Okay, you can see t percentage r will reduce to t. So here, immediately after this reduction, this corresponding semantic action we will perform. So here you can see that this t dot value, this t dot value, you can see t dot value, this will be t1 dot value divided by r dot value. Now t1 dot value, that is 4, r dot value, that is 2. So 4 divided by 2, that is 2. So here you can see this will become 2. Okay, now you have the final reduction, that this is the final reduction. Okay, what is the final reduction? That is, you can see as hashtag t, s has t, this you are reducing to s. So immediately after this reduction, this corresponding semantic action you will execute. So you can see s dot value, here this s is the head. So you can see s dot value, this s dot value, it will become s1 dot value star t dot value. So you can see s1 dot value, that is 40, multiplied by t dot value. T dot value is basically, you can see that is 2. So 40 multiplied by 2, that will be 80. So finally here 80. So remember, the question is asking that the computed value of s dot val for the root node. So tell me, what will be the computed value for s dot val at the root node? S dot val at root, what that will be? That will be equal to 80. Okay, so final answer will be I can say, finally, I can say that, finally, I can say s dot val at root, at root. Okay, this will be 80. So the answer will be 80. I hope you understood. So this method is actually very simple because I'm explaining. So it took time, but actually this will not take time. Okay, if you do it yourself, it will not take much time. Okay, so this is actually very simple method. Now this same question we are going to solve using another method also. Okay, don't worry, I will tell you another method to solve this question. But did you understand this method? Because this is the best method for this question. There is more efficient method also that I will tell you. But remember, if some variation comes, if they do some changes in the semantic actions, then remember this method will always help you. This method will always work. But now I will tell you another method which will work in some cases, not always. Okay, yes or no? But this method will always work. Whenever postfix SDT is given to you, this method will always work. As I told you, evaluation of postfix SDT, this method we have seen, make a parse tree without semantic actions, then you perform left to right depth first traversal and execute the semantic actions along with the reduction of the corresponding production rule. So using this method, this gate exam question, this gate 2022 question we have solved. And what answer we got? We got answer 80. Now, the same question you can solve using another method, that is analysis of the given grammar. If you analyze the given grammar, then the same question you can solve using another method very quickly. Okay, so for that we need to analyze the given grammar. Let's focus on the given grammar now. You can see this is the given grammar. Look at the given grammar. You will find that this given grammar is the unambiguous expression grammar, where this hash is basically same as star. Hash represents multiplication and this percentage represents division. Okay, notice these small things you notice. Basically, hash represents star, hash is basically multiplication, and this percentage, this is basically your division. Okay, yes or no? You can notice this hash is basically multiplication. The meaning of hash, that is multiplication. This is the meaning, hash meaning. And similarly, percentage meaning is basically division. Okay, you can see the meaning of percentage, that is basically division. Okay, and notice one more thing. Look at this grammar. Let me write this grammar here. This is basically s going to s. It's like this, s going to s star t, because I told you that this hash means multiplication. Okay, so this hash, let me replace by multiplication, because already this hash, the meaning of hash, that is basically multiplication. So this grammar is basically s going to s star t, or t going to t division by r, or r going to id. Okay, notice one thing from the previous lectures. If you remember, this grammar, this is basically unambiguous expression grammar. And what is the ambiguous expression grammar corresponding to this grammar? You can see s going to s star s, or s divided by s, or id. Notice this grammar, if you notice, this is a ambiguous expression grammar. This grammar, this is ambiguous expression grammar. Ambiguous expression grammar. Okay, and for this ambiguous expression grammar, what the corresponding unambiguous expression grammar means? From this ambiguous expression grammar, when you remove the ambiguity manually, from this ambiguous expression grammar, when I remove the ambiguity manually, then this unambiguous expression grammar I will get. Yes or no? Basically, you can see from this ambiguous expression grammar, when I disambiguate it, disambiguate manually, or I can say that when we disambiguate this expression grammar disambiguate this expression grammar, then what we will get? Then we will get this unambiguous expression grammar. This unambiguous expression grammar. Okay. Do you remember all these concepts? We have already seen in the previous lectures when we were discussing LL parsers. Okay. In the top down parsing, before studying the top down parsing, we have already seen this, how to disambiguate any expression grammar. If ambiguous expression grammar you have, then how to remove ambiguity from this expression grammar. So this is how, this is the corresponding unambiguous expression grammar. And I told you, from this ambiguous expression grammar, what should I do to remove the ambiguity? Basically, we need to do total two things, or I can say total three things we need to do. You can see this is the recap of ambiguity elimination from the expression grammar. All these concepts we have already seen before the top down parser. This concept we have seen means ambiguity elimination from expression grammar. Ambiguity can be eliminated from expression grammar by enforcing precedence and associativity. Okay, yes or no? Do you remember this? All these concepts? Do you recall? Let's see. You can see by enforcing precedence and associativity, we can remove ambiguity from the expression grammar. And how to enforce precedence? To enforce precedence, we will create labels. Basically, we will create labels for operators with different precedence. Higher level means lower precedence, lower level means higher precedence, and same precedence means same level. Same level means same precedence. Okay, very simple. So you can see, to enforce precedence, we will create labels for operators with different precedence. Lower level means higher precedence. You can see here in this grammar, this is the unambiguous expression grammar. Here you can see that the higher level is star, means multiplication is higher level. Higher level means lower precedence. Lower level means higher precedence. So division has higher precedence than multiplication. Okay. Next, you can see how to enforce associativity. To enforce associativity, we will use recursion. You can see for left associativity, use left recursion. For right associativity, use right recursion. Okay, do you remember? So you can see in our example, in our unambiguous expression grammar, you can see that here this is, look at this star, or I can say look at this production. This is left recursion. Yes or no? S is calling S, and this is left recursion because this S is on the left side. So you can see that this is left recursion. So this star is basically left associative. Similarly, look at this production. T going to T divided by R. Here also T calling T. This is also left recursion, you can see, because this T is on the left side. So here this division is also left associative. Okay, yes or no? So you can see, to enforce associativity, for left associativity, use left recursion. For right associativity, use right recursion. One more thing, you enforce precedence, you enforce associativity. Okay, but after that also, one more thing we need to do to disambiguate the grammar. If you want to make the grammar unambiguous, or I can say that if you want to eliminate ambiguity from the expression grammar, then you enforce precedence, you enforce associativity. But there is third point also. I told you, what is the third point? That is, operators at the same precedence level should either all be left associative or they should all be right associative, else ambiguity might still be there. Means on a particular level, let's assume two operators have the same precedence. So because they have same precedence, so they will be on the same level. Yes or no? For example, addition comma subtraction, they have the same precedence. So if two operators have same precedence, then they will be on the same level. But I am saying that operators at the same precedence level should either all be left associative or they should all be right associative. Otherwise, else ambiguity still might be there. Remember one thing, on different levels, you can have different associativity. For example, let's assume, look at this. In this example, you look at Let's assume that, see, these are two different levels. Okay, you can see this multiplication has lower precedence, higher level means lower precedence, lower level means higher precedence. So notice one thing here, multiplication is basically left associative because left recursion you are using. And for a moment, let's assume that we do this, that instead of t divided by r, let's assume we do something like r divided by t. Okay, let's assume you do something like this. Now you can see that here you are using the right associativity. Okay, this is right recursion, so it means that this division is right associative. So remember, on different levels, if you are using different associativity, that is fine, there is no problem. On different levels the operators can have different associativity, but I am saying that on a particular precedence level, at the same precedence level, all the operators either must be left associative or all the operators must either be right associative. Otherwise, ambiguity might still be there. So basically, this is just the recap of ambiguity elimination from expression grammar. All these concepts we have already seen in the previous lectures. This is just a recap. Now, you can solve this question. You can see this GATE 2022 question. You can solve using the analysis of the given grammar. Okay, so you can see I already told you that this grammar, this is basically unambiguous expression grammar corresponding to this ambiguous expression grammar. From this ambiguous expression grammar, when you remove the ambiguity by enforcing the precedence, by enforcing the associativity, then finally this unambiguous expression grammar you will get. And you can notice this has represents multiplication and this percentage represents division. Okay, now you can solve this question very easily. So let's solve. So by the analysis of this grammar, we have seen that this hash represents multiplication and this percentage represents division. And this grammar that you have, this is basically unambiguous expression grammar. Okay, so you can see S going to S multiplication T or T. Then you can see this T going to T divided by R or R. And then you can see this R is going to ID. Okay, some things you notice here, that higher level means lower precedence and lower level means higher precedence. So here you can see that this star means this multiplication has lower precedence and this division has higher precedence. Okay, so let's talk about the precedence. Let's talk about the precedence. So division has higher precedence than multiplication. Next, let's talk about the associativity. Associativity, you can see here, look at this production. So this is left recursion. So this star, this multiplication is left associative. Look at this production here. This is also left recursion. So this division, this is left associative. So you can see that. Let's talk about associativity. So star comma division both are left associative. Okay, star comma division both are. This is also left associative and this is also left associative. Okay, very simple. I hope you understood. So this expression, this input that is given to you, you can just, you can replace this hash with star and you can replace this percent with division. Yes or no? So basically the input that you will get, 20 star 10 divided by 5 star 8 divided by 2 divided by 2. Okay, correct. One more thing you notice, look at the semantic actions. These semantic actions, they are very intuitive. Okay, this also you notice that all these semantic actions, they are actually very intuitive. For example, you can see that this hash represents multiplication. So s going to s star t, you can see this s dot value, it will be basically s1 dot value multiplied by t1 dot value, or I can say t dot value. Yes or no? So you can see that all these semantic actions, these are actually very intuitive. For example, when s goes to t, then you can see s dot value will be t dot value. Okay, next you can see that this t going to t divided by r, then you can see this t dot value will be equal to t1 dot value divided by r dot value. When this t goes to r, then t dot value equal to r dot value. R going to id, then r dot value equal to id dot value. So notice one thing, that all the semantic actions, these are also very intuitive, or I can say there is nothing fishy here. Okay, When you see the semantic action, there is nothing weird, there is nothing fishy here. Okay, so now let's solve. So this input is given to us, and we already know that the precedence of division is more than this multiplication. So first we will do the division. Yes or no? Before multiplication, this division will be done. This division will be done. Okay, you can see these two division, they are side by side. So here associativity will come into the picture. You can see division, that is left associative, means in these two division, which division we will perform first. So that will be this division, because division is left associative. Okay, you can see according to this given grammar, division is left associative, multiplication is left associative. Okay, so you can see this is what we are going to do. Now what we will get 20 star, this value will become 2 star 8, sorry, you can see 20 star, this value will become 2 star, this value will become 4. Okay, then division by 2. Then again you can see this division has more precedence, so this we will perform. So 20 into 2 into this will become 2. Okay, next you can see that now we will perform the multiplication, and multiplication is left associative. So this multiplication we will do first, so it will become 40 into 2, and finally 40 into 2, that will become 80. This is your answer. I hope you understood. Okay, so this question basically, this gate 2022 question we have done using two methods. Okay, using two different methods. I hope you understood both of them. Okay, let's move on now. Let's solve this gate 2023 question. Consider the syntax directed translation given by the following grammar and semantic rules. Here NIFB, these are the non-terminals. You can see NIFB, these are the non-terminals. And you can see syntax directed translation is given to you, where grammar is given to you, semantic rules are given to you. Okay, this is the syntax directed translation scheme. Notice one thing, this syntax directed translation scheme, is this postfix SDT? Tell me, is this postfix SDT? Yes, this is postfix SDT, because all the semantic rules, they are at the right end of the production bodies. Yes or no? All the semantic rules, they are placed at the right end of the production bodies. So this is a postfix SDT. Okay, now let's see here. The question is saying n is the starting non-terminal. This n, this is the starting non-terminal. Hash 0, 1, these are the lexical tokens corresponding to input letters hash 0, 1. Means for the input letters in your input, string, for these letters hash 0, 1, for these letters we generate these tokens hash 0, 1. Okay, next you can see x dot val. This is the attribute for non-terminal x. So x dot val denotes the synthesized attribute. Don't worry about synthesized attribute, what this synthesized, what it means. This will become very clear when we study SDD, syntax directed definition. I told you SDD, syntax directed definition, and SDT, syntax directed translation scheme. These are two different concepts. Okay, two different concepts. They are related to each other, but they are different. Okay, so right now don't worry about this synthesized. Okay, don't worry about it. It will become clear in the next lecture. So you can see x dot val, this denotes the synthesized attribute, a numerical value associated with non-terminal x. Basically, this x dot val, this is basically attribute corresponding to non-terminal x. Means for this non-terminal x, this val, this is the attribute. Next you can see I1, F1. These denote occurrences of I and F on the right hand side of the production. Okay, for example, here you can notice I going to I1, B. Notice this I1, this is also non-terminal I. Both are same. This is also non-terminal I. This is also non-terminal I. But just to differentiate like which I am talking about, that is the reason we are using this subscript. Okay, for example, here also we have F. Here also we have F. Now, which F I am talking about? Which F are we talking about? So to differentiate between these two F, we are using this subscript 1. Okay, so you can see here that I1, F1, they denote the occurrences of I comma F on the right hand side of the production. And you can see for the tokens 0 comma 1, the 0 dot value is equal to 0 and 1 dot value is equal to 1. Okay, very simple. So you can see this SDTs, this translation scheme is given to you. The question is asking the value computed by this translation scheme for the input string 10 hash 011, what that will be rounded off to 3 decimal places. Now this question is actually very easy to solve. We will solve this question by using two methods. The first method is evaluation of postfix SDT. This given translation scheme, this is a postfix translation scheme. This is a postfix SDT. So how to evaluate postfix SDT, that we already know. Okay, this is the method. You can see evaluation of postfix SDT. Given a postfix SDT, what is the best way to evaluate it? Very simple. We will make the parse tree without semantic actions. Then we will perform left to right depth first traversal. Then we will execute the semantic actions immediately after the reduction of the corresponding production rule. Okay, you can see we will perform the semantic actions along with the reduction of the corresponding production rule. So this is how we evaluate postfix SDT. And you can see in this question, in this gate 2023 question, this SDT that is given to us, this is postfix SDT. Okay, so let's solve this question using this method to evaluate postfix SDT. Okay, so let's solve it. What we will do? First, we will make parse tree without semantic actions, correct? Okay, so let's make parse tree without semantic actions. So in the parse tree, the root node that will be the start variable, that is n. So you can see this n will go to I hash f because I want one hash. Okay, you can see I want hash. So this n will go to I hash f. Okay, next you can see to the left of hash I need 10. Okay, basically here I need 10 and here I need 011. Okay, so this I will go where? This I, you can see I want 10 here. So you can see if I goes to B, then B will go to 0 or 1. So I want 10, so I will go to IB. Okay, I will go to IB. IB. Next you can see that this B, I can say that this B will give me one digit, either 0 or 1. And from here also I need one digit because total, remember, to the left of hash I need only 10. So now you can see that this I will go to B and this B will go to 1. This B will go to 0. Okay, very simple. Now let's see to the right of hash. Here I want 0, 1, 1. So this F will go to BF. Next, you can see this B will go to 0 and this F, it will again go to BF because remember I want 0, 1, 1. To the right of hash I want 0, 1, 1. Now this B will go to 1 and this F will go to B. You can see F will go to B and B will go to 1. Okay, so this is the parse tree that we will get without semantic actions. So this is the step number 1, I can say. Step 1, that is parse tree without semantic actions. Parse tree without semantic actions. Okay, this is the step number 1. What is the step number 2? Now we will perform left to right depth first traversal. Okay, and immediately after a reduction we will perform the corresponding semantic action. Very simple. So let's do this. Okay, so let's go left to right depth first. Okay, let's go left to right depth first. Left to right depth first, and you can see here we got our first reduction. Okay, you can see this 1 is reducing to B. Okay, 1 is reducing to B. So when 1 is reducing to B, then immediately after this reduction we will execute the corresponding semantic action. So the corresponding semantic action, that is B dot value, it will become 1 dot value. 1 dot value is already 1. Okay, so you can see that here this B dot value, it will become 1 dot value, that is 1. So remember this B dot value will basically become 1. Okay, very simple. I hope you understood. So I can write like this, that this B dot value, this b dot value, it will basically become 1. Okay, very simple. Now just keep going. We got our next reduction also. You can see b is reducing to I. Okay, b is reducing to I. So this b, this is reducing to I. So immediately after this reduction, we will perform the corresponding semantic action. So here I dot value will become b dot value. B dot value is already 1. So I dot value, that will also become 1. Okay. Now you can see next, you just keep going until you find the next reduction. You can see we got our next reduction. That is, this 0 is reducing to b. Okay, when this zero reduces to b, then you can see immediately after this reduction, we will perform the corresponding semantic action. So this b dot value will become 0 dot value. 0 dot value, that is 0. That is given in the question. 0 dot value is equal to 0. So you can see this b dot value will become 0 dot value, means this b dot value will become 0. Okay, very simple. Next, you can notice that another reduction we got. What is the next reduction? That is, this ib is reducing to I. Okay, correct. This IB is reducing to I. IB is reducing to I. So immediately after this reduction, this corresponding semantic action we will execute. So you can see that this I dot value, remember this I is the head. Okay, so you can see this I dot value, means this I dot value, it will become 2 I1 dot value plus B dot value. Okay, so you can see this I dot value will become 2 I1 dot value plus B dot value. Okay, you can see I1 dot value, that is 1. So 2 multiplied by 1, that is 2, plus B dot value, that is 0. So 2 plus 0, that is basically 2. So you can see that this I dot value, it will become 2. Okay, we got value 2 here. Okay, now you keep going until you find the next reduction. So just keep going, left to right depth first. Okay, keep going, keep going, keep going. Okay, next you can see we got our next reduction. That is, 0 is reducing to b. 0 is reducing to b. So immediately after this reduction, we will perform this semantic action. So this b dot value will become 0 dot value. So this b dot value will become 0, because 0 dot value is equal to 0. Okay, next you can see, just keep going until you find the next reduction. We got our next reduction. That is, this 1 is reducing to b. Okay, so b dot value will become 1 dot value. So b dot value will become 1. Okay, here b dot value will become 1. Okay, keep going until you find the next reduction. We got our next reduction. You can see we got our next reduction. That is, 1 is reducing to b. So you can see immediately after this reduction, we will perform the corresponding semantic action. So b dot value will become 1 dot value. 1 dot value is 1. So b dot value, that will become 1. Okay. Now you can see we got our next reduction. You can see b is going to f. This is the next reduction we got. B is going to f. Okay, b is going to f. So basically this b is reducing to f. So immediately after this reduction, we will perform the corresponding semantic action. What is the corresponding semantic action? We will execute this. So f dot value will become half of b dot value. B dot value is 1. So half of 1, that is basically half. Yes or no? So here remember, f dot value will become half. Okay, f dot value will become half. Now you keep going until the next reduction. The next reduction we got, this is the next reduction. You can see that bf is reducing to f. Okay, so you can see that this bf, this is reducing to f. Okay, so this bf, this is reducing to f. So immediately after this reduction, we will execute the corresponding semantic action. We will perform the corresponding semantic action. So here this f dot value, what it will become? You can see this f dot value, f is the head, remember. Okay, this f1 is this, and this f is the head. So f dot value, that will become half of b dot value plus f1 dot value. So remember, you can see here b dot value, that is 1, because this bf, this is reducing to f. Okay, so you can see that this b dot value, that is 1. F1 dot value, that is half. 1 plus half, that will be 3 by 2. Okay, now you can see this f dot value, this will become half of that. Okay, so that will be 3 by 4. Yes or no? So you can see that for this f, what will be f dot value? that will be 3 by 4. Okay, how we are getting this 3 by 4? Basically, you can see f dot value will be equal to half of b dot value, that is 1, plus f1 dot value, that is half. Okay, so finally you can see what we got. So inside you can see this got 3 by 2 multiplied by 1 by 2, so that is basically 3 by 4. Okay, very simple. Now let's see the next. We got another reduction. The next reduction we got, you can see the next reduction we got this bf, this is reducing to f. Okay, so now you can see again this bf, this is reducing to f. So immediately after this reduction we will perform the corresponding semantic action. So what will be this f dot value? This f is the head, so you can see this f dot value, this will be half of b dot value plus f1 dot value. So remember, what will be f dot value here? That will be half of, that will be half of b dot value plus f1 dot value. Remember, b dot value, that is 0, and f1 dot value, that is 3 by 4. Okay, yes or no? So half of 3 by 4, so that will be 3 by 8. Okay, very simple. And finally you can see this is the last reduction that we got. This is the last reduction, and you are reducing I has f to n. This I has f, this we are reducing to n. So immediately after this reduction, this corresponding semantic action we will perform. Okay, so you can see for this n, what will be n dot value? What will be n dot value? That will be equal to I dot value plus f dot value. I dot value, that is 2, that is 2, plus f dot value, that is 3 by 8. Okay, yes or no? So 2 plus 3 by 8, that will be your value computed by this translation scheme for the input string. So finally you can see that what will be your answer? N dot value, that will be equal to, you can calculate this. Okay, 2 plus 3 by 8. Okay, you can take your calculator and you can calculate. So let me see. You can say 3 divided by 8 plus 2. So we got this value, that is 2.375. Okay, this is your answer. I hope you understood. Very easy, right? This question, it's very easy. I hope you understood this. The complete analysis that we have seen so far, I hope you understood. Okay. Now, the same question we are going to solve using another method also. So let's see the method number 2 to solve this question. The method number 2 to solve this question by analysis of SDT. Okay, basically, we will do the analysis of these semantic actions. We will do the analysis of this complete SDT. We will do the analysis of the grammar, analysis of the semantic actions, and then we will see what this SDT is basically doing. Once you find out what this SDT is actually doing, then you can easily solve the question. Whatever input is given to you, you can very easily solve it. Yes or no? So let's do the analysis of this SDT. In this SDT, few things you notice, few things you observe. First thing you observe is that B is going to either 0 or it is going to 1. So you can see this B is either 0 or 1. Basically, the digits that we are using, these are either 0 or 1. Yes or no? So remember, the digits that are used, digits are basically either 0 or 1. Do you agree? Means, can I say that input is basically binary number? Can I say input will be a binary number? In this question also, you can see input is a binary number. Yes or no? Okay, so one thing you can notice, that input is a binary number, because this B is either going to 0 or B will be going to go to 1. So the digits that you are using, that is either 0 or 1. Okay, so I can say that input is basically binary. I can say input is basically binary. Now you might be thinking, what is the meaning of hash? What is this hash? What is this? Okay, because here you can see that n will go to I hash f. Okay, n will go to I hash f. So what is this hash actually? Actually, if you notice, you can get only one hash. Did you notice? You cannot get more than one hash, because n will go to I hash f. Then after that you can never get hash. It's like this, that n will go to I hash f. Now you can notice, now here a binary number you will get, here a binary integer you will get. Okay, yes or no? Here a binary number you will get, I can say, and here also a binary number you will get. Do you agree with me? And if you notice this hash, this is only one, exactly one time. This appears exactly once in the input. Yes or no? This hash actually appears exactly once in the input. Let me tell you, this hash is basically your decimal point, or I can say binary point or radix point. Okay, this hash basically, let me tell you, this hash, this is basically your radix point, or I can say binary point, or I can say decimal point. Okay, so basically this is your radix point. Let me tell you, this hash is basically your radix point, or I can say binary point. Okay, this is your binary point, and you can notice this I, n is going to I hash f. This hash is basically your point. Okay, this is like point. Okay, point. And let me tell you, this I means the integer part, and this f means the fraction part. Okay, yes or no? This I means the integer part, and this f means the fraction part. This is the integer part, and this f means the fraction part. Okay, is this clear? Are you getting what is happening here? I hope you understood that basically your input is basically integer part dot fraction part. Okay, your input is like that. Is this clear? For example, you can see our input. If you look at our input, that was 10 hash 011. That is basically same as 10.011. Okay, is this clear? This was your input, and you can easily notice that everything is very simple here. You can notice that what we are doing, if you have your input, for example, basically if your input is like this, that I dot f, if this is your input, I'm not using hash now because hash is the dot. Okay, you already know hash is basically the dot. Hash means hash means dot. Okay, so you can see that if this is your input in binary, of course, okay, this input is in binary, that you know, this is a binary input. Now tell me, if you convert this binary input to decimal, if I convert this to decimal, then convert to decimal, just apply your concepts from the digital logic subject, from number system. How do we convert binary to decimal? Very simple. We convert this integer part separately and this fraction part separately. Yes or no? Do you remember? Basically, we will find the decimal of integer part. We will convert this integer part separately. Plus, we will convert this fractional part separately. Yes or no? We will find the decimal of fractional part, and then we will add them. Yes or no? This is the overall decimal for the input. Do you agree with me? So you can notice the same thing we are doing here. You can see that n dot value. What is n? N is I dot f. So what will be n dot value? This n dot value, this represents the decimal value. Actually, for all the non-terminals, this VAL, this attribute represents the decimal value. Okay, let me tell you here. You can see for all the attributes. Okay, let me tell you, for all the non-terminals, for all non-terminals. Here, notice one thing. For all the non-terminals, this val attribute, this val attribute, val attribute represents, val attribute actually represents decimal value, corresponding decimal value. Okay, is this clear? The val attribute actually represents corresponding decimal value, equivalent decimal value, I can say. Okay, I can say that this val attribute represents equivalent decimal value. Equivalent decimal value. So for example, this and dot val, this will represent the decimal value for the entire input. Okay, for the entire input, what is the decimal value? Okay, you can see this and dot val. If your input is, of course, your input is I dot f, this is your input. Okay, this is the input. Now remember this and dot val, it represents, this is the decimal value for the entire input. This is the decimal value for entire input. Okay, and remember this I dot val, it represents I dot val, it represents decimal value for the integer part. Okay, is this clear? This is the decimal value for integer part. And what about this f dot val? What about this f dot val? This is the decimal value for fractional part. This is the decimal value for fractional part. Okay, and what about this b dot value? What about this b dot value? This is the decimal value. This is the decimal value for a single binary digit, for a single bit. Okay, for a single bit, of course. Like if your single bit is 0, then for 0, what will be the decimal value? That will be 0. And for 1, what is the decimal value? That will be 1. Is this clear? Okay, so you can see for bit 0, what is the decimal? That is 0. And for bit 0, the decimal is 0. For bit 1, the decimal is 1. Okay, I hope you understood this so far. Now very simple. So remember, if your input is I dot f, if your input, that is integer part dot fractional part, of course this input is in the binary. Okay, now notice what we are doing. Basically, you are basically finding the decimal, the equivalent decimal for this input. Okay, for this binary input, what will be the decimal value? This is what you are finding. And you can notice that here in these two, look at these two rules. In these two rules, we are converting the integer part to decimal. Okay, and notice in these two rules, okay, so one by one let's discuss. You can see using these two rules, and of course this. Okay, so let me tell you that using these, we are converting the integer part to decimal. Okay, so these we are using, remember these we are using, to find, okay, these we are using, these will find, to find decimal of this integer part. Okay, and you can see actually it is very easy to understand. See why these rules are coming from, where these rules are coming. So it is actually very easy to understand. Notice, if I give you in the integer part, if I give you a single digit, you tell me, like if I give you 0, let's assume I is equal to 0, then tell me what will be the decimal. Say very simple thing I am asking. On one side I will write the integer part, I will write on one side. On another side I will write the equivalent decimal. Okay, so you tell me, If the integer part is a single digit, single bit like 0, 1, then what will be the decimal part? What will be the decimal equivalent? If the integer part, for example, if the integer part is 0, then the decimal will be 0. If the integer part is 1, decimal will be 1. Yes or no? This is the corresponding decimal for this integer part. Okay, so very simple. Now tell me a simple point. For example, if I do like something like this, that okay, 1 1, then what it means? It means that whatever was the previous decimal value for this one, whatever was the previous decimal value, that you will multiply by 2 plus this value. Yes or no? It will happen like this. Do you agree with me? What I'm saying is this, that let's assume that for some integer part I1, already the decimal value you have already found. Okay, let's assume that is that decimal value you have already found, and that is m. Okay, for some integer part I1, the decimal value you have already found. If this is your integer part I1, your integer part, if that is I1, then the equivalent decimal will be m. Now a very simple question I'm asking you, you tell me the answer. If I do this I1 0, now tell me what will be the decimal for this I1 0. If this is your integer part I1 0, then what will be the decimal? Very simple. What you will do? This you will multiply by 2 plus 0. Yes or no? 2 I1 plus 0. And if I ask you for this I1 1, what will be the decimal? What that will be? Very simple. This I1 you will multiply by 2 plus this one as it is. Okay, yes or no? The same thing we are doing here. Notice one thing. Here also the same thing you are doing. If I is going to B and B will go to a single binary bit. Yes or no? Okay, I is going to B and B will go to a single binary digit. So you can see that I dot value will be same as B dot value. But notice, when this I is going to I1B, when this I is going to I1B, now what will be this I dot value? What will be the decimal value of I1B? So the decimal value of I1B, that will be equal to twice the value of I1 plus the value of B. Yes or no? You will multiply this I1 by 2 plus the value of B. Okay, so did you understand this? Very simple. This I am asking what will be the decimal? What will be the decimal of I1, I1B? So what that will be? That will be equal to 2 multiplied by decimal of I1 plus decimal of B. Yes or no? Plus a decimal of B. Okay, that same thing we are doing here in these rules. I hope you understood. Okay, I hope you understood how these rules are converting this integer part to decimal. Okay, very simple. Now let's see how these rules, like this rule, how these four rules, how they are converting. Or let me do like this, that okay, these two and these two, how they are converting the fractional part to decimal. Okay, so basically your input, your binary input, that is I dot f. This is your binary input. Okay, now you can see that using these two, using this and using this, using these two, what we are doing to find decimal of the fractional part. Okay, of the fractional part, correct? Now here notice one thing. When we find the decimal of the fractional part, then what are the weights? You can see, like, let me give you one example. Okay, consider this input. Let's assume your input is let's assume 0.1011. Then here you can see that this is the fractional part. Okay, yes or no? This is the fractional part f. This is your fractional part f. Correct? Now you can notice here how to convert this to decimal. How to convert this to decimal? You already know the weight of this. This is basically 2 power minus 1. The weight here, this is 2 power minus 2. the weight here is 2 power minus 3, and the weight here is 2 power minus 4. So what will be the decimal? That will be 1 divided by 2 plus 0 divided by 2 power 2 plus 1 divided by 2 power 3 plus 1 divided by 2 power 4. Okay, yes or no? Do you agree with me? This will be your decimal. Very simple. So now notice, now using this idea, you can see how we are getting these rules. Okay, let's focus on these rules. So you can see, if our fractional part is a single bit, let's assume, okay, on one side I am writing the fractional part. On one side, let me write the fractional part. On another side, let me write the decimal, the equivalent decimal. Okay. Now, if the fractional part is, let's assume, 0, then what will be the decimal? If the fractional part is only 0, then what will be the decimal? You can see what is the weight of this 0, because remember, ultimately we have this point f. Okay, we have this point f, means if you have point 0, then what is the weight of this 0? That is 2 power minus 1. So can I say the decimal will be 0 by 2? Can I say like this? Okay, similarly, if the fractional part is 1, means point 1. See, if you have point 0, if you have point 0, then in the decimal, what you will get? In the decimal, you will get 0 divided by 2. If you have point 1, then in the decimal, what you will get? In the decimal, you will get 1 by 2. Yes or no? So you can see, in the if the fractional part is single bit, if the fractional part is 1, then it will be, the weight is 2 power minus 1. The weight is 2 power minus 1. That means 1 by 2 into 1. Okay, yes or no? That same thing you are doing here. Notice, when this f is going to b and b will go to a single bit, look at these. F is going to b will go to a single bit. So you can see this, if you have a single bit, if the fractional part is a single bit b, okay, single bit b, here this b is the single bit. Okay, so if the fractional part is single bit b, if the fractional part is single bit b, then what will be the decimal? That will be 1 by 2, whatever is b dot value. Yes or no? Is this clear? So you can see that this is clear, that f going to b, so f dot value will be 1 by 2 b dot value. This is clear. This is very simple. Okay. Now let me ask you a very simple thing. Let's assume already you know that for this f1, for this fractional part f1, let's assume the decimal value you already know, and the decimal value, let's assume that is p. Okay. For this fractional part f1, if the fractional part is f1, means dot f1, then the decimal equivalent, that is p. Now you tell me, if I put 0.0 f1, or I can say that point b f1. Okay, point b f1. Now tell me what this value will become. You can see, for this f1, if you have point f1, means if the fractional part is f1, then the equivalent decimal value will be p. Now what I'm doing, I'm doing point b f1. So you can see this b, this will have weight 1 by 2. And if you notice, for this f1, what will happen? For every bit in f1, the weight will, for every bit in f1, the weight will divide by 2. Yes or no? Okay, in this f1, now in this, when you do this point bf1, now notice this b, it will have weight 1 by 2. And for every bit in f1, the weight will divide by 2. Yes or no? So you can see overall what will be the decimal equivalent. That will be 1 by 2 b plus whatever is the value of f1, that will basically divide by 2. Yes or no? Is this clear? So ultimately I can say that 1 by 2 b, 1 by 2 b value plus 1 by 2 f1 value. Okay, so I can say it will be 1 by 2 b value plus 1 by 2 f1 dot value. Okay, and this is the same thing that is written here. You can see f dot value equal to 1 by 2 b value plus f1 value. Okay, I hope you understood this. Let's let me just quickly give you a simple example. For example, let's assume that f1, this fractional part. Okay, fractional part. On one side, let me write the fractional part. Just to give you one example, if some students did not understand, then don't worry. Okay, on one side fractional part, on another side decimal. What are the decimal equivalent? Now, for example, if the fractional part is, let's assume, 1 1 0, or maybe 0 1. Okay, take 0 1. So you can see if this is your fractional part, what that means, what that basically means, what will be the corresponding decimal? You can see 0.01. What will be the corresponding decimal? That will be 1 by 2 0 plus 1 by 4 1. Yes or no? It will be basically, it will be this value, let's call it p, and that value will be 1 by 4. Yes or no? That value will be 1 by 4. That you already know. Now notice, let's call this f1. I am calling it f1. Okay, now I am calling it f1. So now you notice, if I ask you what will be dot bf, like if the fractional part is, let's assume, bf1. If this is the fractional part, bf1. Okay, this is what I'm asking. If the fractional part is bf1, now you can see if the fractional part is, let's assume, bf1, means this bf1, then what will be the decimal value? You can see this is a single bit, so the weight is 1 by 2, so it will be 1 by 2 b dot value. Okay, b dot value plus notice one thing, it is like bf1 and f1 is already 0 1, so it will be basically dot b01. Okay, now notice every bit in f1, its weight will divide by 2. Now you can see for this 0 the weight will be 1 by 2 square. For this the weight will be 1 by 2 power cube. Yes or no? So basically overall what will happen? You can see here, for this 0 the weight was 1 by 2. For 1 the weight was 1 by 2 square. But notice here, for this 0 the weight is 1 by 2 square. For this 1 the weight is 1 by 2 cube. So you can see that in this f1, for every bit the weight is divided by 2. So overall you can see what we will get. Whatever was your f1 value, whatever was your f1 value previously, whatever was your f1 value previously, it will basically divided by 2. Yes or no? It will be divided by 2. I hope you understood. So you can see in this situation, the decimal value, what that will be? That will be 1 by 2, whatever was b dot value plus whatever was f1 dot value previously. Okay, I hope you understood this. So very simple. So finally, I can say that what this grammar is basically doing, or I can say this SDT, this syntax directed translation scheme, this is basically what it is doing. It is converting the binary to decimal. Okay, I hope you understood this point, that this is basically converting binary to decimal. Okay, I hope you understood. So finally, now you can solve this question very easily. Your given input, what was that? That was 1 0 hash 0 1 1. This was the given input. Now you can easily find the output. Okay, you can see, because this is same as 10.011. Now you can convert to decimal. So if you convert to decimal, what you will get? 1 0 in the decimal, it will be 2 plus. What about 0 1 1 in the decimal? What it will become? It will become 1 by 4 plus 1 by 8. Okay, so finally you can calculate, you will get your value, you will get your answer. Okay, I hope you understood. So this is the complete analysis of this question. Let's all get 2000 question. Consider the syntax directed translation scheme. SDTs, syntax directed translation scheme, is given to us. Assume attribute evaluation with bottom up parsing, means attributes are evaluated immediately after a reduction. Notice one thing, this SDTs, this is a postfix SDTs. Do you agree with me? Because all the semantic actions, they are at the right end of the production bodies. So notice that this is basically postfix SDTs. This is postfix SDTs. And I told you one thing, that when you have postfix SDTs, then how to evaluate postfix SDTs, that is written here. You can see that attributes are evaluated immediately after a reduction. Okay, this actually I told you that in the postfix SDTs, the semantic actions we execute along with the reduction. The semantic actions are executed immediately after a reduction. Yes or no? So that is what is written here. Now, using this SDTs, there are two parts, part A, part B. The part A is saying using this SDTs, construct a parse tree for the expression 4 minus 2 minus 4 into 2 and also compute its E dot value. This is the part A. And part B is asking it is required to compute the total number of reductions performed to parse a given input. Using synthesized attributes only, modify this SDTs without changing the grammar to find what is E dot read. RED means reduction, means basically E dot read. That means the number of reductions performed while reducing any input to E. Okay, both the parts we will solve. So let's focus on part A. You can see the given SDTs, this is actually postfix SDTs because all the semantic rules they are placed at the right end of the production bodies. And for postfix SDTs, how to evaluate it? So you can see the evaluation of postfix SDT. The method we have already seen. Method is very simple. Make a parse tree without semantic actions. Then you perform left to right depth first traversal and execute the semantic actions along with reduction of the corresponding production rule. Means when you reduce a production rule, then immediately after reducing this production rule, the corresponding semantic action of that production rule we will perform, we will execute. Okay, so this is how we evaluate a postfix SDT. Now we can solve this question very easily. So you can see this is the given postfix SDTs, or I can say this is the given syntax directed translation scheme. And what the question is asking in the part A, that the input is 4 minus 2 minus 4 into 2. Okay, so let me write the input here. The input is 4 minus 2 minus 4 into 2. 4 minus 2 minus 4 into 2. Okay, this is the input. Now let's solve this question. So the method only for postfix SDT, we have this method that semantic actions are executed immediately after a reduction. Okay, first you make the parse tree without semantic actions. Then you perform left to right depth first traversal, and whenever you make a reduction, then immediately after that reduction, the corresponding semantic action you perform. Okay, very simple. So let's make the parse tree without semantic actions. So you can see in the parse tree, the root node that will be the start variable E. Okay, what I want 2 minus and 1 star. I want 1 star, so E will go to E star T. Okay, E will go to E star T. Okay, E will go to E star T. Next, you can see that I got 1 star I got. Now what I want? To the left of this star, I want 2 minus. So remember, this T will go to 2. Ultimately, remember this T will go to F, this T will go to F, and F will go to 2. Okay, because to the left of star, I want 2 minus. Okay, so you can see that this E, where it will go? You can see this E will go to T. Okay, because I don't want another star. So E will go to T. Now this T will go to F minus T. This T will go to F minus T. Okay. So I got one minus, I want another minus. If I want another minus, so what I need to do? This T will go to F minus T. This T will go to F minus T. I got 2 minus. That's it. This is what I want. So now you can see that this F, it will go to 4. Okay. Now this F will go to 2. This T will go to F, and this F will go to 4. Okay. Is this clear? That's it. So you can see what we got. We got our parse tree without semantic actions. So this is the step number 1. Okay. Step number 1 is done. Now, after this step number 1, what we will do? we will traverse left to right depth first. Okay, and whenever there is a reduction, then immediately after that reduction, we will perform the corresponding semantic action. So you can see we are going left to right depth first. Okay, keep going, left to right depth first, keep going. Now you can see that here you got your first reduction. Okay, our first reduction we got. So you can see that this 4 is reducing to f. 4 is reducing to f. So immediately after this reduction, the corresponding semantic action we will perform. So you can see this f dot value will become 4. Okay, here f dot value that will become 4. So I can say that this f dot value here is basically 4. Okay, keep going till you find the next reduction. Keep going till you find the next reduction. We got our next reduction now. You can see this is the next reduction. This 2 is reducing to f. Okay, 2 is reducing to f. You can see. So this 2, it is reducing to f. Immediately after this reduction, the corresponding semantic action we will perform. So you can see f dot value that will be 2. Here I can say f dot value that will be 2. Okay, f dot value that will be 2. Is this clear? Very simple. Now you keep going until you see the next reduction. Okay, keep going. You can see we got our next reduction. The next reduction that we have, that is, you can see f is going to, this 4 is reducing to f. 4 is reducing to f. So immediately after this reduction, the corresponding semantic action we will perform. So f dot value will be 4. Here I can say that f dot value, it has become 4. Then we have another reduction also. We have another reduction. You can see f is reducing to t. F is reducing to t. So immediately after this reduction, we will perform the corresponding semantic action. So t dot value will become f dot value. You can see t dot value that will become f dot value. F dot value is 4. So t dot value will become f dot value, that is also 4. Okay, we got another reduction. What is that? Another reduction. You can see that is this another reduction. Look at this another reduction, that is f minus t is going to t. F minus t, it is reducing to t. Okay, so here you can see immediately after this reduction, the corresponding semantic action we will perform. And you can see that this t dot val, okay, in this semantic action, you can see this t dot val. This t is the head, remember, and this is t1. So you can see t dot val means this t dot val, this is equal to f dot val minus t dot val. Okay, f dot val that is 2 minus t dot val that is 4. So you can see 2 minus 4, that will be minus 2. So you can see that this t dot val, this is actually minus 2. Okay, then you can see we got another reduction. We got another reduction. What is this? Here again you can see f minus t is reducing to t. F minus t is reducing to t. So you can see immediately after this reduction, the corresponding semantic action we will execute. So you can see this t dot val. This t dot val, t is the head. So remember this t dot val, this t dot val, this will be equal to f dot val minus t1 dot val. F dot val that is 4 minus t1 dot val that is minus 2. 4 minus minus 2. So you can see this t dot val, this will become 6. Okay. Next we got another reduction. We got another reduction. This t is reducing to e. This t is reducing to e. So here immediately after this reduction, the corresponding semantic action we will perform. So you can see e dot value will be equal to t dot value. So here e dot value that will be equal to t dot value, that is 6. Okay. Keep going until you see the next reduction. Keep going left to right depth first. Keep going, keep going. Yes, we got our next reduction. Okay, you can see this next reduction we got. Here you can notice that this 2 is reducing to f. Okay, this 2 is reducing to f. So immediately after this reduction, this corresponding semantic action we will perform. So f dot value will be equal to 2. Here f dot value that will become 2. We got the next reduction, that is f is reducing to t. F is reducing to t. So here you can see f is reducing to t. Immediately after this reduction, the corresponding semantic action we will perform. So t dot value will be equal to f dot value. F dot value is 2. So t dot value will be 2. Then we got our last and final reduction. That is, you can see e star t is reducing to e. You can see this e star t that is reducing to e. So here e dot val, you can see e dot val, e is the head, remember, Okay, this is E1. So you can see E dot val, that will be equal to E1 dot val into T dot val. Okay, so you can see E dot value, that will be equal to E1 dot value into T dot value. So that will be 6 into 2, that will be 12. So you can see here, this value will be 12. Okay, this value will be 12. So that's it. So you can see at the end, what is E dot val? I can say that E dot val for the root node, that will be equal to 12. Okay, E dot val at the root node, what is E dot val? That is equal to 12. I hope you understood this. Okay, so this is how you can solve this question. The same question I can solve using another method also. So let's solve the same GATE 2000 question, part A. We are discussing part A. This part A you can solve using another method, that is method 2 to solve this question, that is analyze the given grammar. Analyze the given grammar and you can solve this question using another method. So notice, look at the grammar here. In the grammar you can see that this star means multiplication and this minus means minus. Okay, star is star, minus is minus. Okay, one more thing you notice, that in this grammar it's like this, that E is going to E star T or T, T is going to F minus T or F, and F is going to 2 or 4. Just look at this grammar and you will recall something. What is that? Look at this grammar and you will recall that this is the unambiguous expression grammar. For which ambiguous expression grammar? You can see, look at this ambiguous expression grammar, like using these two operators, star comma minus, like E star E or E minus E or 2 or 4. Okay, so you can see this grammar, this is ambiguous expression grammar. Look at this. This is a ambiguous expression grammar. Okay, correct. This is ambiguous expression grammar. And when you eliminate the ambiguity from this ambiguous expression grammar by enforcing precedence and associativity, you will get this unambiguous expression grammar. Yes or no? You can see, when you disambiguate, when we eliminate ambiguity, I can say that eliminate ambiguity. Eliminate ambiguity. When you eliminate ambiguity, then this unambiguous expression grammar you are going to get. Unambiguous expression grammar you will get. And I told you this point when we were discussing how to eliminate ambiguity from expression grammar. When we were discussing this topic, then I told you how we can eliminate ambiguity from expression grammar. What we do to eliminate ambiguity from expression grammar, you can enforce precedence and also associativity. By enforcing precedence and associativity, we can eliminate ambiguity from the expression grammar. Okay, so you can see this is the recap of ambiguity elimination from expression grammar. I told you that ambiguity can be eliminated from expression grammar by enforcing precedence and associativity. To enforce precedence, what we will do? We will create labels for operators with different precedence. Lower level means higher precedence means lower level, or I can say higher level, lower level, higher precedence. And if two operators have same precedence, then they will be on the same level. Okay. And you can see, to enforce associativity, for left associativity, use left recursion. For right associativity, use right recursion. So you can see ambiguity can be eliminated from expression grammar by enforcing precedence and associativity. You can enforce precedence by creating labels, lower level, higher precedence, higher level, lower precedence. And same precedence means same level means same precedence. To enforce associativity, for left associativity, use left recursion. For right associativity, use right recursion. One more thing, remember, after enforcing precedence and associativity, one more thing is important. That is, operators at the same precedence level, they should either all be left associative or they should all be right associative. Okay. On same level, if you have multiple operators, then they will have same precedence. But if you want to eliminate the ambiguity, then remember, on same precedence level, all the operators, either all of them must be left associative or all of them must be right associative. If you don't do this, means on a particular precedence level, if some operator is left associative, some operator is right associative, then ambiguity might still be there. Okay, so basically these are the three rules I can say. If you want to eliminate ambiguity from expression grammar, then these are the three rules: enforce precedence, enforce associativity, and also when you are enforcing precedence and when you are enforcing the associativity, then remember, on the same precedence level, all the operators must be left associative or all the operators must be right associative. Okay, on different levels the operators can have different associativity. Okay, there is no problem, but on the same precedence level, all the operators must be left associative or all the operators must be right associative. Okay, now let's solve this question. Once we have done the analysis of the grammar, now you can easily see that this grammar is basically like this, that E is going to E star T or T is going to F minus T or F is going to 2 or 4. Okay, now notice one thing: higher level, lower precedence, lower level, higher precedence. So you can see here this multiplication is at the higher level. So this has lower precedence. So notice one thing. Let's talk about precedence. So here you can see this multiplication, this is at the higher level. So it has lower precedence, lower level, higher precedence. So you can see subtraction has more precedence than star. Okay, because subtraction is at the lower level, higher precedence. Let's talk about associativity also. Okay, so let's talk about associativity. You can see that, look at this production. In this production, we have left recursion. E is going to E. Okay, so this star is left associative. Star is left associative. Okay, and look at this production. T is going to F minus T. T is going to T, but this T is at the right position, rightmost position. So this is actually right recursion. So this subtraction is right associative. Subtraction is right associative. Okay, is this clear? Let me know. Very simple. So very simple. You can see. Okay. So from this grammar, you can easily see the precedence of subtraction is more than multiplication, and associativity, this multiplication is left associative and subtraction is right associative. Now you can easily solve this question. What was our input? Our input was 2 minus 4 minus 2 into 4, I think something like this. Okay, 4 minus 2 minus 4 into 2. 4 minus 2, 4 minus 2 minus 4 into 2. Yes, this was our input. Now you can easily solve this question. So you can notice that minus has more precedence than star. Okay, so before this star you will do minus, and this subtraction is basically right associative. So this subtraction will be done first this will be done. Okay, so what we will get, we will get 4 minus, we will perform this subtraction first, means 2 minus 4, that is basically minus 2 star 2. Next, again you can notice that this subtraction has more precedence than star. So now we will do this. Okay, so here 4 minus minus 2, that will be 6 star 2, that will be 12. Okay, the answer will be 12. I hope you understood. So this is how you can solve this question. This is another way to solve this question. So that's it. Okay, so the part A we have seen. Now let's see the part B. The part A is over. Now let's see the part B. That is, in the part B, the question is asking, it is required to compute the total number of reductions performed to parse a given input. When you are parsing a given input, then we need to compute the total number of reductions. How many total number of reductions will be performed to parse a input? This is what we need to compute. Now the question is asking that, using synthesized attributes only, Don't worry about synthesized attributes right now. When we discuss SDD, syntax directed definition, then it will become very clear what is synthesized attribute, inherited attribute. Okay, right now don't worry about it. Just use your intuition. Just use the logic, just use the intuition, nothing else. Okay. So basically using synthesized attributes only, modify this SDTs. We need to modify this because notice one thing, in this SDTs, some value you are calculating. Yes or no? The value of the expression you are calculating. In this given SDTs, we are calculating the value of this given expression, assuming that subtraction has more priority than multiplication, and subtraction is right associative and multiplication is left associative. So assuming these things, we are calculating the value of this expression. Okay, yes or no? I can say that this given SDT, notice one thing, this given SDT, what this SDT is doing, this is basically what is it doing? What is the work? What is the work that this is doing? Okay, the work is basically compute expression value, compute value of the expression. It is basically computing expression value, value of expression. It is computing the value of expression with some assumptions, with some assumptions, with subtraction having more priority than multiplication, and subtraction being right associative and multiplication being left associative. Okay, yes or no? This is what this given SDT, this is what this is doing. It is computing the expression value basically. Now what we need to do? We need to compute the number of reductions. Okay, now the question is saying we need to compute the number of reductions, total number of reductions we need to compute. So we need to modify the given SDTs. These rules we need to modify, but without changing the grammar. You cannot change the grammar. You can change the rules. Of course, we need to change the rules. These semantic rules we need to change because using these semantic rules, you are basically computing the value of the expression. You are calculating the value of the expression. But what we need to do, we need to calculate the total number of reductions performed to parse a given input. So without changing this grammar, you change these semantic rules and you calculate, you compute the total number of reductions. Basically, you find e dot read. The question is using this red, this attribute, to count the number of reductions. Okay, with non-terminals, with these non-terminals, we are using this attribute red. This attribute is basically used to count the number of reductions. For example, e dot read, this is the number of reductions performed while reducing an input to e. When you reduce any input to e, then what is the total number of reductions performed? That is represented by e dot red. Okay, is this clear? So similarly, we will use, for example, f dot red. What it means? F dot red means when any input you reduce to f, then what is the total number of reductions performed? Similarly, we will use t dot red, means whenever any input you reduce to t, then what is the total number of reductions performed? That is t dot red. I hope you understood. So you can see what is e dot red. This is the number of reductions performed when you reduce any input to e. When any input you reduce to e, then what is the total number of reductions performed? That is represented by e dot red. This is what this is what is captured by this red attribute of non-terminals. I hope you understood. Okay, so let's see what we are going to do now. First, let me tell you. First, let me tell you that with all these non-terminals, we will use the attribute red. Okay, so you can see for any non-terminal, like if you have a non-terminal x, let's assume if you have a non-terminal x, non-terminal, let's assume x. Of course, what this x can be? This x either can be e, or this can be f, or it can be t. Yes or no? That you know. Okay, so you can see if you have this non-terminal x, then for this x, we introduce attribute red. Okay, what this x dot red, what it means? It is basically the number of, it is basically the number of reductions, the number of reductions performed when an input reduces to x, reduces to x. Okay, means whenever any input will reduce to x, okay, then what is the total number of reductions? Okay, the total number of reductions, that is your x dot red. Okay, is this clear? The total number of reductions, that is your x dot red. I hope you understood this. Okay, and what we need to calculate? We need to calculate basically e dot red. Okay, so what we are going to do now? It is very easy. It is very common sense. See, nothing else. Notice, with every production rule, let's write the semantic action. Okay, the semantic action that we will write, we will keep in our mind that we need to calculate the total number of reductions. Yes or no? Okay, so you can see what I will do. First, let me write all the productions. E is going to E1 star T. This one, this subscript one, I'm using just to differentiate between this E and this E, nothing else. Okay, so this is there, then you have E going to T, this is there, then you have T going to F minus T, F minus T1, then we have T going to F, then F going to 2, and F going to 4. Okay, so these are the productions. Now notice one thing, I will start from the bottom. Okay, basically from the basic things I will go towards the more, I can say, recursive things. So you can see from the basic things, let's start. Okay, you tell me, simple things I am asking. Look at this production and you tell me what will be f dot red corresponding to this production. Corresponding to this production, what will be the semantic action? See, semantic action, you tell me, like, what will be f dot red? What will be f dot red corresponding to this production? Corresponding to this production, I want the semantic action. So tell me, when you reduce 4 to f, then total how many reductions are performed? Tell me. Very simple. When you reduce this 4 to f, then total how many reductions are performed? Total number of reductions. Tell me. You tell me total number of reductions. What is that? That will be 1. Yes or no? Because this 4 is already a terminal. Yes or no? This is already a terminal. So you cannot go below it. Yes or no? You cannot go below it. So you can see that when you reduce 4 to f, when you reduce this 4 to f, then total number of reductions performed, that is equal to 1. So I can say that corresponding to this production rule, what will be the semantic rule? That will be f dot red equal to 1. Very easy. Yes or no? Similarly, you can notice that corresponding to this also, f dot red will be equal to 1. Yes or no? So you can see that for these simple productions, for these simple reductions, you can see f dot red, here also it will be 1. And if 2 is going to f, then also f dot red is equal to 1. Okay, because you already know that when 2 is going to f, when this 2 is going to f, then of course this 2 is already terminal. So it's not like you cannot, you can go below it. Yes or no? You cannot go below 2. Yes or no? Because 2 is already a terminal. Is this clear? So you can see that corresponding to this production and corresponding to this production, we have the we have the semantic rule. Okay, now you tell me about this next one. Just tell me about this next one. Here, what should I write? You can see, very simple question I'm asking. When this f reduces to t, then total how many reductions will be there? I am asking total how many reductions will be there when t is reducing to when f is reducing to t. What is the total number of reductions? I am asking total number of reductions not only for when f is reducing to t, actually when some input is reducing to t. Please notice this definition here. In this definition, please notice what is x dot red, that is the total number of reductions performed when some input is reducing to x. Okay, when some input is reducing to x. Is this clear? Okay, when some input is reducing to x, then what is the total number of reductions? Okay, now I am asking a very simple thing. F is reducing to t, so what will be t dot red? What is t dot red? T dot red means, first of all, let me ask you, what is t dot red? You can see t dot red, that means when some input will reduce to t, then what will be the total number of reductions? So very simple, remember, f is not a terminal, yes or no? This is non-terminal, so of course we will not stop here. Do you agree with me? This f is non-terminal, so definitely we will not stop here. When some input will reduce to t, then what is the total number of reductions performed? Okay, the same thing here, you can see some input. Okay, when some input is reducing to x, then what is the total number of reductions performed? That is x dot red. Okay, so here you can see that this f is basically non-terminal, so definitely this at this f we will not stop. Okay, we will go to, maybe we will go to 2 or we will go to 4, but overall the point is, maybe we will go to 4, maybe we will go to 2, but overall the point is that the t dot red, that will be equal to one reduction is this, plus whatever is the number of reductions to reduce the input to f. Do you agree with me? Okay, do you agree with me that, see, some input will reduce to f and then this f will reduce to t. So you can see when this input is reducing to t, then what is the total number of reductions? That is t dot red. So that is equal to one reduction here plus whatever is the number of reductions to reduce this input to f, that is your f dot red, that is captured by f dot red. So finally I can say that corresponding to this production, what will be the semantic rule? That will be, you can see t dot red, that is equal to 1 plus f dot red. Do you agree with me? Means one reduction is this, one reduction is this, plus whatever is the number of reductions to reduce the input to f. Okay, the input you are reducing to f, so for that you have some number of reductions, then one more reduction is this, so that is the reason you can see t dot red, that is equal to 1 plus f dot red. Okay, yes or no? Is this clear? Now let's see the next. So you can see we got this, here we got t dot red is equal to 1 plus f dot red. So far you understood? Now let's see the next. Now let's see this one. You can see t is going to f minus t. Again you can see when this f minus t, when this reduces to t, when this f minus t, when this reduces to t, then one reduction is this. Okay, yes or no? One reduction is this. One reduction is this. But notice, you can notice that this f is non-terminal, this t is non-terminal. So definitely f is like some input was reducing to f, some input was reducing to f, and some input was reducing to t. Yes or no? So overall, I can ask you, when the input is reducing to t, then what is the total number of reductions? That is t dot red. So that will be equal to, what is f dot red plus what is t dot red plus this one more reduction. Yes or no? This one reduction we have plus, because remember, when the input will reduce to t, then what is the total number of reductions? That will be equal to, when input is reducing to f, some input is reducing to f, then what is the total number of reductions? That is captured by f dot red. When some input is reducing to t, then what is the total number of reductions? That is captured by t dot red. Then one more reduction we have. So I can say that this t dot red, that will be equal to f dot red plus t1 dot red plus 1. Yes or no? Okay, is this clear? So finally I can say that this is what we got, that this t dot red, that is equal to, you find f dot red plus t1 dot red plus one more reduction. Okay, so similarly you can find for here also, you can see that one reduction is this, and whatever is the number of reduction to reduce some input to t. Okay, yes or no? So you can see that here e dot red, that will be equal to 1 plus t dot red. Okay, and what about here? So you can see that this e dot red, that will be equal to, remember one reduction is this, one reduction is this, plus some input is reducing to e1. So what the total number of reduction that is captured by e1 dot red? Okay, plus some input is reducing to t. So what is the total number of reductions performed that is captured by t dot red? Okay, that's it. So finally, this is your syntax directed translation scheme to calculate, to compute the total number of reductions required to parse a given input. Okay, is this clear? I hope you understood. That's it. This is the complete analysis of this GATE 2000 question. Part A, Part B, both we have done. Okay, I hope you understood. So in this lecture, in this session, we have done some GATE PYQs based on SDT, syntax directed translation scheme. Based on SDT, all the GATE PYQs that have come so far, we have solved. Each and every GATE PYQ based on SDT, we have solved. Okay. In the next lecture, we will study SDD, syntax directed definition, and also we will solve the GATE PYQs of SDD. Okay. Okay. Thank you, everyone. This is a doubt one student is asking, so let me answer it. This is the given grammar, and the student is asking what are the precedence and associativity of different operators. Okay, so here you can see, let's talk about the associativity. This arrow, what is the associativity of this arrow? So you can see, look at this production. In this production, this is left recursion, e is calling e, and this e is at the leftmost position. So you can see this is the left recursion. So this arrow is basically left associative. For left associativity, we use left recursion. And you can see this minus, this is right associative because e is calling e. This e is on the rightmost position. So here this minus, this is actually right associative. Right associative. Also you can see this here. You can see here this star. Okay, this star is basically right associative. This star is right associative because here you can see that this t is going to f star t. Okay, what about this plus? Look at this plus. Here actually t is going to f plus e. Here actually we did not enforce any associativity for this plus. Okay, you can see e will go to t, then t will go to f plus e, then this e will go to some. Actually, if you notice one thing, this plus 2 plus will come side by side. Can they come? Let's see. You can see this plus when it can come side by side, because remember when we are discussing associativity, then the operator should come side by side, yes or no? So here actually if you notice, if you want 2 plus to come side by side, then what you need to do, you need to do something like this, that as this e will go to t, then this t will go to f plus e. So far we only have 1 plus, but remember we are discussing associativity, so let's bring another plus side by side. Okay, so you can see this e can go to t, this e can go to t, and then again this t can go to f plus e. So basically it will happen like this, that this e can go to t, okay, and then this t can go to f plus e. Okay, similarly if you repeat this process, then what will happen? then you can see that this again this E will go to T, T will go to F plus E. Okay, so it's like this. So basically this plus is basically right associative here. You can see when you are discussing associativity, then the operator should be the same operator. When you are discussing the associativity of plus, for example, I am discussing the associativity of plus. So you bring this plus side by side. Okay, now actually you can notice that this plus is basically right associative here, because you can see it's like this, that E will go to T in the parse tree. Look at the parse tree. In the parse tree, E will go to T, T will go to F plus E, then again this E will go to T, then this T will again go to F plus E. Okay, so you can see that basically this plus is right associative. What is the reason? Because you can see that this plus will be evaluated first, yes or no. You can see this plus will be evaluated first, and then this plus will be evaluated, yes or no. Okay, so you can see that first this plus will be evaluated, then this plus will be evaluated. Here also you can see first this will be evaluated, then this, you can see, then this, and then this. Okay, so like that. So you can see that plus is basically right associative. Okay, so this is actually a very good question from the associativity point of view. Okay, in this question, in this grammar, actually we cannot directly judge. Okay, because you can see that, you can see we don't have left recursion, we don't have right recursion. Okay, actually notice one thing, that this F will simply go to A. Okay, F will simply go to A. Actually notice that this is basically right recursion, because this T is going to E, E is going to T. So this is indirect right recursion. Notice what is happening here. This E is going to F plus E. This T is going to F plus E. Of course this F will go to A, that's it, nothing else. Okay, nothing this F can do. So you can see that now this E is going to T. Okay, notice now this E is going to T. So you can actually see that there is indirect right recursion here. There is indirect right recursion here. Okay, so that is the reason here. I hope you understood this explanation. I hope you understood this explanation. The two explanation, I hope you understood that this plus is basically right associative, because you can see this T will go to F plus E, then this E can go to T. Yes or no? This E can go to T. So ultimately it's like T is going to F plus T. Okay, overall it's like T is overall going to F plus T. Overall T is going to F plus T. Indirectly, of course, this is indirect right recursion. If you remember, we have discussed this left recursion, indirect left recursion, elimination of indirect left recursion when we were discussing the top-down parser. At that time, we have discussed indirect left recursion. Similarly, here this is indirect right recursion. Yes or no? Okay, when we were discussing top-down parser, there direct left recursion, indirect left recursion, elimination of indirect left recursion, these concepts we have seen. Similarly here this is indirect right recursion. Okay, indirect right recursion. Okay, so you can see this is basically indirect right recursion. Okay, I hope you understood. So this is the associativity. Okay, it's very simple. A star is basically right associative, and all the operators, the associativity we have seen. Okay, and what about precedence? So the associativity we have seen that plus is basically right associative. Okay, now let's talk about the precedence also. Let's talk about the precedence also. So here you can see that higher level, lower precedence, lower level, higher precedence. So you can see that these two operators, they have the same precedence. These two operators have the same precedence. So you can see that higher level, lower precedence, lower level, higher precedence. So it's like plus has the same precedence as star. Okay, plus and star, they have same precedence, and they have more precedence than this operator and minus. Minus comma this operator, they have the same precedence. Okay, Very simple. One more thing, let me tell you here. I told you that when you eliminate ambiguity from expression grammar by enforcing precedence, by enforcing associativity, then one more thing you should take care. What is that? It should happen that at the same precedence level, all the operators must have the same associativity. You can see that on this precedence level, all the operators have right associativity. That is very good. Okay, but notice, look at this precedence level. Here, this operator, this arrow operator has left associativity and this minus has right associativity. So you can check, I think this grammar is ambiguous. Remember, from any ambiguous expression grammar, to eliminate ambiguity, we enforce precedence, we enforce associativity. But there is one more thing, that is, when you enforce precedence and associativity to eliminate the ambiguity from the expression grammar, then remember, at the same precedence level, all the operators must be left associative or all the operators must be right associative. Okay, so you can see in this level, we have two operators which have different associativity. So can you check this grammar? I think this grammar is still ambiguous. Okay, this grammar is still ambiguous. You can check. So here actually you can take this string. Let's take this string a minus a arrow a. Take this string a minus a arrow a. For this actually you will get two parse tree. Okay, let me show you that for this you will get two parse tree. What are the two parse tree? Notice, it will be one parse tree will be like this, that okay, e can go to e arrow t, then you can see that this e will go to, then you can see that this e will go to t minus e. Okay, so then finally you can see this t will go to f and this will go to a, this e will go to t, this will go to f, this will go to a, this t will go to f, this will go to a. So you can see what we got. We got a minus a arrow a. Okay, this is what we got. Another parse tree, let me show you, that will be t minus e, and then you can see that this e will go to e arrow t. Okay, so now you can see that this t will go to f, this f will go to a, this will go to like this, and sorry, this e will go to e arrow t, this is t, e arrow t. Okay, so you can see that finally this t will go to f and this will go to a. So you can again see here a minus a arrow a minus a arrow a. Yes, that's it. So you can see that for this we have two parse tree. Okay, did you notice that for this we have two parse tree, two parse trees? This is what I was telling you. I was telling you that this grammar is still ambiguous. Okay, this grammar is still ambiguous. Why? This grammar is still ambiguous. Can you tell me why? What is the reason? Did you notice why this is still ambiguous? Notice, we have enforced associativity. Every operator, for every operator, we have enforced associativity. We have enforced precedence also. We have enforced associativity. We have enforced precedence. Both are enforced. But still this grammar is ambiguous. Why? But still this grammar is ambiguous. Why? Because on the same precedence level, some operator is left associative, some operator is right associative. This is the problem. Yes or no? Why? Because on same precedence level, on same precedence level, on same precedence level, some operator is left associative, some right associative. Okay, is this clear? So that is the reason this grammar is still ambiguous. Okay, and you can see for this string you will get two parse trees. For this string we will get two parse trees. I hope you understood. So this is the complete analysis of this grammar. Okay. I hope you understood. Remember how to eliminate ambiguity from expression grammar by enforcing precedence, by enforcing associativity. These concepts we have seen when we were discussing top-down parser. There, these concepts we have seen. All the gate PYQs we have done, all the concepts we have seen, everything we have already seen. But this question is a very beautiful question because here, how to find the associativity of plus? You can see there is a indirect right recursion. Okay, you can see. So the associativity of plus, that is right associative, because there is a indirect right recursion. Okay, so this is a beautiful question. Okay, I hope you understood the complete analysis of this grammar. Okay, thank you everyone.